Hi everyone, my name is Sylvia. I'm a PhD student at the University of Toronto, and I'm going to be presenting a joint work with Anna Dodik, Professor Theodore Kim, and Professor Amanda Phillips. Now, let's start with a universally loved example, airport security. Okay, well, it's safe to say that nobody's experience with airport security is pleasant, and definitely some people have it harder than others. But for now, I just want to focus on most people's experience with these sort of full-body scanners that you see at airports. Now, I would venture that most people experience is like this. You enter the scanner, you put your hands above your head, you wait for about 10 seconds or so, and then you exit the scanner. It might be a little bit invasive, but at least it's very straightforward, right? Well, here's what that experience is like for many gender non-conforming people like me. We enter the scanner, put our arms above our head, wait the same 10 seconds, then the security agent stares confused at their screen and fidgets with their screen for a while, put our arms above our head again, wait 10 more seconds, then there are more moments of confusion. The agent maybe calls for their superior, we wait for their superior to come around, then both agents look at the screen, they're confused, sometimes they're even laughing. Then they tell us to put our arms above our head again, same deal. They talk among themselves for a bit. Then they may call for even yet another agent, back to hands above head, 10 seconds, optional laughter, and repeat and repeat. And at this point, they finally ask us to step aside from the scanner, and they do the worst of all, which is they do a public, very invasive pat down. And then they go back to talking amongst themselves, and finally, they let us leave. Now, why is it that most people breeze through these scanners, while gender non-conforming people like me have to go through all this dehumanizing process? Well, when someone walks into the scanner, here's what the security agent sees. Basically an empty screen with two buttons that are labeled scan. One of them is pink, one of them is blue. So how this works is if the agent sees a man in the scanner, they'll press the blue button. And if they see a woman in the scanner, they'll press the pink button. The software has a specific model of what a man's body looks like and what a woman's body looks like. And according to which button the agent presses, it will try to match your scan data and fit it to the corresponding model. And of course it goes off if it finds any anomalies, if the fit isn't good enough. Now, since many of us have bodies that do not perfectly fit their model of a male body or their model of a female body, then the scanner will go off regardless of which button they press. So that's the immediate reason why we have to go through all that trouble. But let's take a step back. The perspective that we really want to convey in this talk is that the reason we have to go through all that dehumanizing process is, at some point in the research and development stage, a scientist or an engineer made a modeling decision to include gender as this binary variable that the security agent has to input. And I'd like to note that this is a choice, a deliberate choice. If the goal is accuracy, they could have modeled a different model for tall people and a different model for short people, or a model for adults and a model for children. All those have undeniably different body shapes. But instead of doing that, the scientists chose sex, or they chose gender, as the sole disambiguation variable in the model. You don't have to select anything else, just pink or blue. And that design decision meant that they excluded many trans people like me from interacting with this technology entirely. Now, this isn't just ethically bad or annoying for us every time we have to go through an airport. This is a technical limitation. You are presenting a piece of software that is failing by design for a segment of the test population. And this situation isn't limited to airport scanners. When gender non-conforming people like me interact with technology, we are constantly faced with models that exclude us. So when I set up my Fitbit, I'm told to input my sex so that the calorie computation is more accurate. Now, I have no idea which one to pick here, so I guess I'll resign myself to the technology being less accurate for me. And the same if I want to order a t-shirt from Amazon, my body has to be masculine or feminine, no middle ground. And same thing when I try to edit this talk's audio in Adobe products. Now, some of these may sound trivial or unimportant, but as our lives become more increasingly intertwined with technology, these modeling decisions made by researchers around sex and gender can be very consequential, as much as blocking people from accessing medical care or even government services. So let's turn our focus to the research community that we are all a part of, which is the SIGGRAPH one. Now, sex and gender appear prominently in the SIGGRAPH research literature. If you're used to reading SIGGRAPH papers, I'm sure you can recall reading sentences that sound like these. So, not only are these decisions consequential, graphics researchers at SIGGRAPH are certainly making modeling decisions around sex and gender. And graphics algorithms are no longer relegated to relatively harmless applications like animated films or video game production. Our algorithms are more and more being used in other fields like artificial intelligence or medicine or security. So it's because of all these reasons that we think it's urgent to take a closer look at sex and gender in the SIGGRAPH research literature. So here's our project statement. We want to 1. Observe the current use of sex and gender in the SIGGRAPH literature, and 2. Analyze the potential harms and scientific limitations that it introduces. Now, my co-author Anna will cover the analysis part of this in a moment, and I'll briefly go now through our observation. To study the role of sex and gender in the SIGGRAPH technical paper track, we did a full survey of every paper presented at SIGGRAPH, that includes SIGGRAPH Asia, by the way, since 2015, and we searched for keywords related to sex and gender. We found 64 works, or about 4% of all SIGGRAPH technical papers since 2015, which makes some mention of sex or gender. So we read each of them. Now we provide a supplemental which enumerates and categorizes all 64 of these. However, in this talk we're going to redact them, since our intention is to analyze the decisions that we, broadly as a community, as a graphics research community, are making. And we don't want to criticize or analyze specific works, or let alone specific authors. And by community, we mean the entire community, which is not just restricted to authors, but includes reviewers, it includes editors, it includes session chairs. So what are our observations? Well, let's begin with the nature of sex and gender as a variable. Of all the works that mention sex and gender, we found 70% of them use it as a binary variable, while 30% don't specify the type. Now, these numbers are easy to add up, 70 plus 30. Crucially, what they mean is that we found 0 works that acknowledge the existence of gender non-conforming people like us. So, for example, works on human parametric modeling that use sex or gender will produce a male model or a female model, and they won't allow for body models that combine features from both. Where does sex and gender appear in technical papers? Where its use it varies a lot. So some papers use sex or gender to report on the diversity of their data set, something like, our data set has 10,000 men and 10,000 women. Some of them use it to report the makeup of their user study participants. So we tried our algorithm on 10 people, 6 of them were men, for example. And finally, some of them use it as actual algorithmic variables that are either inputs or outputs in a proposed model. Finally, we identified 2 works that propose using image-based binary gender classifiers. To study what all these observations mean, I'll turn it over to Anna.
It is easy to feel that there is something wrong with the current usage of gender and sex in computer graphics research. But for this presentation, we wanted to approach these questions in a more concrete manner. So how do we frame the observations that we made? What do they mean for our discipline? And how do we think about the real-world harm that they produce? Going back to our survey, why did we even settle for this specific set of 7 observations in the first place? Well, this work uses the tools given to us by the algorithmic fairness community. Several authors provide frameworks for categorizing algorithmic bias and its impact. In our analysis, we have applied two frameworks, one for analyzing the types of bias and the other one for analyzing the harms that result from it. The framework suggested by Suresh and Gutag in 2021 categorizes bias based on where it occurs in a system's life cycle. We also personally found it to be very useful for talking about bias in a technical context. So let's start with the obvious one, representation bias. This type of bias refers to certain groups being underrepresented by a data set or in a user study, for example. Concretely, imagine you are collecting a dataset consisting of scans of human bodies or faces. There are two ways in which representation bias can occur. The first one, which often comes to mind, occurs because uniformly sampling a population will lead to very few representative samples for underrepresented groups. Now, in this example, the turquoise population is far underrepresented compared to the other groups. So assuming we draw uniform, reasonably stratified samples, we should expect to see 8 times fewer samples representing that population. Now, if we, for example, average some characteristic across our samples, the turquoise population will contribute very little to that mean. There is, however, another form of representation bias, and that is a biased sampling procedure. In this scenario, while you might think your sampling distribution is uniform over the entire population, once you look at the data you have collected, it is clear that there was a sampling bias present. Now, let's look at some stats together. Globally, the estimates of the percentage of trans and non-binary individuals are between 0.1 and 2% of the population, with reported prevalence rising in places where being trans is more accepted. In a hypothetical dataset of 1,000 people, there should have been between 1 and 20 trans and non-binary people. Now, adding up all of the participants across all of the datasets and user studies mentioned in our survey, there was far more than 1,000 total participants. However, the papers in our survey report 0 trans or non-binary participants. Even more concerning is the fact that 0 papers ever notice or mention the existence of such a bias. Moving on to historical bias, it occurs when researchers or developers introduce biases which are historically present in some culture into a system. A good example of where historical bias occurs are gender classifiers. Such systems tend to misclassify people who do not conform to strict societal gender norms, which can include trans and non-binary people, but also includes everybody whose gender expression is slightly different from societal norms. Moving on to measurement bias. Now, looking at a typical machine learning pipeline, one of the most important decisions the algorithm designer makes is what the inputs and the outputs of the model should be. It is precisely here in deciding what features to include and what the target variables should be that measurement bias is introduced. Measurement bias can be introduced by either inaccurately measuring a variable, by, for example, using a binary variable to represent something as diverse as gender, or it can be introduced by incorrectly measuring a variable. In the case of gender, this can be, for example, using labelers to decide a person's gender based on an image, or using a gender classifier to do the same job. Lastly, something we kept seeing over and over again is the usage of proxy variables. So the thing is, most often, gender is not actually the variable you want to use. To explain what we mean by that, we found that authors often use gender as a shorthand for some combinations of voice pitch, body proportions, presence or absence of makeup, commonly co-occurring bodily or facial characteristics, and so on. Which leads us naturally into omitted variable bias. So let's say you include gender as a variable in your model and you get good results. This could make you conclude that gender is really successful as a variable. However, its success might stem from the fact that it correlates with some other important feature that has been omitted from the model, such as, for example, self-expression or physical features. As a consequence, gender and sex are likely not as discriminative when the result is also conditioned on things like, for example, hair length or hip width or voice, pitch, speech patterns, and so on. In cases where we found sex and gender used in papers and justified by an assumed improvement in accuracy, we found no attempt to identify if the success was due to omitted variables or not. And lastly, using gender as a variable might actually work worse for those populations where the correlation is not as strong or is in fact negative, whereas something like hair length might work well for anybody. So to illustrate the point about omitted variables, there was a paper that went somewhat viral because the authors claimed it could identify a person's sexual orientation from photos. In a follow-up analysis, all it took to flip the algorithm's classification of the people in these photos from straight into a classification of gay was to slightly tweak the camera angles and the presentation of the participants. As the authors of the follow-up point out, a number of important variables were omitted, making it seem like the algorithm was detecting sexual orientation, whereas it was detecting things like the presence of makeup. Note that something like the presence of makeup or camera angle might correlate with gender in the same way. Evaluation bias is bias that is encoded and propagated by the benchmarks we use for evaluation. So as an example, using a binary gender model for evaluating something orthogonal like virtual try-ons, or evaluating virtual avatars on a face model that's biased against gender diverse people. To summarize our thoughts on this, if we codify biased benchmarks as a community, we encourage methods that conform to the biases in those benchmarks. And lastly, bias can also creep in during a system's deployment or after publication, if you will. So a common example of this are feedback loops, where let's say there's a virtual try-on system and it will be less likely to be used by non-binary people if it works poorly for them. And then if developers improve an algorithm based on its performance during deployment, it's possible that the algorithm will continue to get worse for non-binary people, who will then in turn be even less likely to use it. Additionally, researchers should be aware that a biased system can sometimes lead to changes in user behavior. An example, a biased voice processing software could cause trans people to consciously alter their voice in order to make the system work better for themselves. This not only causes harm, but can also lead to inaccurate results in perceptual and user studies. Lastly, all research builds upon already existing work, and as a consequence, leaving bias for future work is likely to propagate that bias further. So there are two high-level conclusions here. The first one is that bias occurs at every stage of an algorithm. This means that the responsibility is very much on every single one of us as computer scientists to think deeply about the choices we make every day. The second one is that bias is a technical limitation, and that it is due time we start treating it as such. Our evaluations need to include algorithmic fairness metrics, and at the very least, the authors need to discuss how their algorithm might be biased against gender and sex diverse people. Our field is increasingly used in downstream applications, so it is important to understand the real-world harm that comes with that. Barocas provides us with a useful framework for discerning the different types of harm that can occur as a consequence of bias. Representational harms refer to the perpetuation of stereotypes that subject people to denigration. An example of that would be the airport security scanners from the beginning of this presentation. Allocative harms, on the other hand, happen when a population is denied access to a resource due to bias. For example, a biased virtual try-on experience might exclude precisely the people who would most benefit from not having to go to physical changing rooms. In summary, I want to turn your attention to SIGGRAPH's stated goal of being a model for inclusion, equity, access, and diversity. We are confident that this work represents the first step towards making the stated goal a reality when it comes to sex and gender diverse people. Thank you.